little bit.
Why did you have
I never punched you that. That's like my line is like just that.
Ow.
Yes, I was sick.
There are more unexcused students than excused students. That is so unusual for this class. Usually you guys are so great.
Well, a lot of kids went to Spain, but I don't know why they would be unexcused.
Not everybody has learned to love Spain. Please not. Literally means what were you saying? Oh, it's Zoom?
No, you and I should do
So who's on the Zoom? Yeah.
I can teach you the fly.
The Spain trip people are. Isn't it great to be rich? I guess. Like, the people who come back often ask, isn't it great to be rich if you just take school off and go to another country?
We can even bring a team and get the 20 games and like whenever you get like efficient.
Yeah, I'm like, don't. I know what you're saying. I love getting me down, but I want to eat an apple on
Probably not. Don't worry. Don't worry. Come up in the future, things will change. Maternalistic well. You're never going to escape it.
So if you increase age, it doesn't get better.
It doesn't. You're going to leave college with massive student debt and you're going to be like, I just graduated. I'm going to buy a Beamer.
I think you want to buy.
Okay, here we go. In this system, guys, there's something very important to talk about, and we'll get to it in a little bit. Increase H2. If you're increasing H2 on this side, equilibrium is going to shift to the left, and that's going to change the amount of CO2 which is here. CO2 is going to be made less because the equilibrium is shifting away from it. If you increase H2O, equilibrium is going to shift over to the right, and that's going to increase the amount of CO2. If you cooled the system, cooling the system is taking away heat. Equilibrium is going to shift to remake some of that heat. Equilibrium is going to shift to the left, and CO2 is going to decrease. If you remove O2, just like removing heat, remove O2, equilibrium will shift to the left, and we're going to reduce the CO2. Then there's the catalyst. What does a catalyst do?
Substance speeds up the reaction, but
Exactly. Yeah, a catalyst speeds up the reaction. In fact, I actually asked Alexa earlier today, and it was pretty cool, so I want you to hear what she said. Alexa, what is a catalyst?
The noun catalyst is usually defined as a substance that causes or accelerates a chemical reaction without itself being affected.
Isn't that cool? So yeah, so a catalyst is something that accelerates the rate of a chemical reaction. Which chemical reaction? Forward or reverse? Both. Exactly. It accelerates both. So does a catalyst change equilibrium? No change. No change. A catalyst accelerates both the forward and reverse reaction. So it doesn't change the equilibrium. Okay? Shall we move on? Please. I hate these arrows. I have arrow issues. Okay. So, at equilibrium, the forward reaction and the reverse reaction are happening at the same rate. Now, I'm going to give you rate equations, we're not going to do anything with them until next month, but I'm going to show you what they are. The rate equation for the forward reaction is a constant, some constant, multiplied by the concentration of the reactants raised to some powers. Okay? This is called the rate law for the forward reaction. It's the concentration of A raised to something, multiplied by the concentration of B raised to something, multiplied by a constant. Again, we're not going to do a lot with the rate laws until May.
Speaking of rates, rate this video.
Yeah.
That's right.
You get rated on the
Strange rate.
Smash that like button, ring the bell,
And it's May.
leave a non-racist comment.
No copyright comments either.
Okay.
No one racism in my sociology.
That's right.
I'm getting sick of it.
This isn't Xbox Live. Okay. Next, if this is the forward reaction, what do you think the reverse reaction has in it?
The exact same thing, but it's backwards.
Yeah, it's got the same thing but C and D.
Dang.
It's got the same thing but C and D. So the rate forward is some value K, we'll say K forward, multiplied by the concentration of A raised to something, multiplied by the concentration of B raised to something. And the rate reverse is constant reverse multiplied by the concentration of C raised to something, and concentration of D raised to something.
So the constants aren't the same?
No, they're not.
Okay.
Now here's the thing. At equilibrium, the forward rate and the reverse rate are the same.
So those equal.
So you can set them equal to each other. You can set them equal to each other and something interesting happens. You got a big K value, which is the ratio of KF and KR. Are you paying attention?
Yes.
It's going to be KR, C, I'm just going to make this a little c, and D, I'm going to make this a little d, over KF, A, and I'm going to use this a little a, and B raised to a little b. Because they're equal to each other. Can you see that if they're equal to each other, you can divide one by the other and get a number? Okay. I'm going to call this KEQ, and then I'm going to take the KR and the KF, and I'm going to squish that together into one experimentally determined value just called K. And this is the equilibrium expression. So I'm going to divide that K out into this K and just make it this. Concentration of the products over the concentration of the reactants. Again, we have these little K values. We're going to divide them out, stick them into this big K value, and just make it concentration of the reactants under the concentration of the products. There actually is a cool Wi-Fi app where you can actually see what it's seeing, but the battery drains in like 10 minutes. It's using wireless. Maybe this summer I'll put together something that will actually, I don't have to worry about anything with the ceiling.
Skin camera.
Okay, now, there's some rules. Are you ready for the rules? If it's KEQ, which is the equilibrium expression, you only use aqueous species in a KEQ. You will have no solids, no liquids, or no gases in a KEQ. Only aqueous species. if it's Kp, that stands for pressure, then it's only gaseous species. If you have a KEQ with aqueous species, in equilibrium with aqueous species only uses aqueous species. In equilibrium with gaseous species only uses gaseous species. For now. When you get to your junior level chemistry, when you're pre-med or pre-pharmacy, then you'd be like, but there's also, but we're not going to worry about that. For this class, and for all foreseeable classes that I'm going to teach, the KEQ, gases only deal with gases, aqueous species only deal with aqueous species, and solids and liquids we don't care about at all. Capiche? Okay. So, what if the KEQ is larger than 1? What does that mean about the fraction? If your KEQ is larger than 1, what does that mean about the fraction?
The concentration of the products is greater than the concentration of the reactants.
Exactly that. So if your KEQ is larger than 1, the concentration of the products is larger than the concentration of the reactants, and we say it is product favored. This equilibrium is product favored, meaning there's more equilibrium, there's more products at equilibrium than there are reactants. So if your KEQ is larger than 1, we say it is product favored because there's more concentration of products than there are reactants. And the opposite's also true. If your KEQ is less than 1, we say it is
Reactant favored.
reactant favored. Way to go, front row. The rest of you guys wake up. I can't help it. You're so boring. You're so boring, and I was watching Desperate Housewives reruns until 3 o'clock this morning. No. You're playing Fork Knife?
Heck no. I was watching Vanderpump Rules.
Of course.
Jose, are you?
Okay, question? Oh my God. No question? All right, so moving on. Okay, give me a thumbs up if you're ready to move on. Okay, next. Now that we know what equilibrium expressions are, let's write some. So, based on this reaction, let's write the equilibrium expression. The equilibrium expression will start quite simply, K equals a fraction. So, see if you can figure out what goes in the numerator and what goes in the denominator. What goes in the numerator? What goes in the denominator? If I had one, I would give you a potato. You don't even need a calculator.
I just need to be a gator.
Yeah.
You just need to know that. I know. I was just trying to go up this rad. You start.
Okay, so I take it from the chatter that you're ready to move on?
Yes.
So what's going to go in the numerator?
The concentration of SO2 to that.
The concentration of SO3, and it's going to get raised to the second power. That coefficient is going to become the coefficient in a chemical reaction becomes an exponent in the equilibrium expression. So SO3 raised to the second power. If you're curious about why that is, why it gets raised to the second power instead of just multiplied by 2, you're welcome to take chemistry AP next year. Right now, just accept it. And then what's going to go in the denominator? SO2 concentration and O2 concentration. Now, I wrote them as concentrations because I don't want to make things too confusing, but sometimes you'll also see them as pressure of SO3 squared and pressure of SO2 squared and pressure of O2. That's also K. I just made them this way because we're learning equilibrium expressions. If you take chemistry AP, we'll write them that way. But just realize that's what we're going to do for now. Okay. If your equilibrium expression kind of looks like my equilibrium expression, give me a thumbs up. If your equilibrium expression needs some help, put your hand up and wave it around so you can ask questions. All right, one more. Take a look at this guy.
Take a look at this.
Peep this. Aim your looking balls at that. Don't take out your balls. That makes two of us.
Oh, dude, me too.
That makes three of us.
As far as you look like,
You
guys
No, I do not have any enchanted water buckets.
Enchanted water buckets? I'm breaking the head on my water bucket.
Okay, so it sounds like from the chatter you're ready to move on.
Yes.
What did you put in the numerator?
H3O.
H3O plus concentration, what else?
HSO3.
HSO3 concentration. Okay, does that look right?
Yeah.
Did you use any exponents?
No.
Why not?
There's no
coefficients.
No coefficients. What did you put in the denominator?
H2SO3.
H2SO3. Anything else?
H2O.
No.
No, it's not active.
You're not gonna, yeah, did you guys hear that? You're not gonna put H2O in the denominator because the H2O is not aqueous. In your equilibrium systems, it's either all gaseous or all aqueous. No liquids or solids. Yes?
So why did you put the H3 on you guys' numerator?
Because it's the first product.
Products over.
Aqueous, one product over reactants. Okay. How are we doing so far? Can we flip the script and go the other direction? Can you write a chemical reaction based on an equilibrium expression?
100.
Let's give it a try. This is going to start with an equilibrium symbol and stuff on the left and stuff on the right. Yes.
So, how you know how H2 you don't put it in references? How do you know if there's going to be like one like that and then like going backwards?
You don't. Well, you don't right now. What you're going to do is you're going to write your chemical reaction. You're going to say, huh, there's something on the left that isn't on the right. Let's see if we can figure it out. That's what's going to show up right here if we have time. It's an excellent question. I can't remember if there's anything like that. I don't think there's anything like that on the test in this class. It will show up in AP if you take AP. You'll be like, something's missing. Okay, it sounds like from the chatter you're ready to move on?
Yes.
So, what did you put in the reactant side? H2 and I2. Did you use any exponents or coefficients or anything like that?
No.
Okay. What'd you put in the product side?
2HI.
2HI. Good. So, and these are all gases in case you're wondering. So, Michelina asked, how would you know if there's something missing? Like, if there's a liquid or a solid in the chemical reaction? You'd write your expression and you were like, something's missing. And you figure out what that missing thing is. Okay, level 2. Something in the reaction, something might be in the reaction that doesn't show up in the equilibrium expression. Okay, Chris is already done. What are you waiting for? It should be more like Chris.
Obviously, a water.
Chris is too good. What do you mean?
Yeah.
Boom, I'm done.
He's too close.
There's like mainstream, honors, and Chris. And somewhere in there, yeah, somewhere in there there's Jameson. Sometimes Jameson gets over here. Sometimes Jameson's up here. Sometimes.
That chart is
Wow, I'm sorry, but I'm
Good to know. You need to get a stamp.
medium speed instead of extremely fast.
Okay, what did you put in the reactant side? What did you put in the reactant side?
2H2O plus 2Cl2.
H2O plus
2Cl2.
2Cl2. And what did you put in the product side?
O2 plus
4HCl plus O2. Okay.
0.2.
Does your chemical reaction look like mine?
Yes.
Yes. Does it matter which one you're in?
Because these are all gaseous species. So we're talking about water vapor. Water vapor. Water can be a gas.
Yeah, no, I don't watch. That's how I spent
I'm the clay. Where's that vapor?
Where's that vapor? Yeah, bro. We're looking for a Walmart. They're always next to Walmart.
What are?
Vape shops.
Oh, yeah.
You're looking for vapors? Just find a Walmart. They're always next to the Walmarts.
Or Albertsons or
GameStop and vape shops are always next to
You know
Walmart.
what's also next to Walmart's a lot?
Rednecks.
That too.
Oh,
Mr. Biker.
What do they do?
I love Walmart. It's like the zoo, but instead of lions and tigers, they have rednecks without teeth. If you've ever been accused of lying through your tooth, you might be a redneck. Okay, what did you put in the reactant site here? NH3
NH3 plus
plus
H2O.
H2O. So this is one of those times where, that's weird. If you write the NH4 over here and the OH minus over here, you immediately realize that you've got an O and two H's that are missing. So that's where you write your H2O. Now, like I don't believe you're going to be tested on this, but it is something that's kind of handy to know. If you are missing something, you can easily figure out what thing is missing, and that thing is either going to be a liquid or a solid. Make sense?
Yes.
All right.